Hi, folks. Next, in our list of things to talk about is current. So, in the first four sort of pieces, we talked about charge and fields. Then we talked about Gauss's law. Then we talked about electric potential. And then we talked about capacitance. And in all four of those sort of units, all four of those chapters, we were considering electrostatics, charges at rest. And no, it's true that we talked about the acceleration of particular charges in electrical environments set up by other charges, or in electric environments just because the environment exists, right? Some electric field accelerates a charge. What is its acceleration? So no, that wasn't charges at rest. But the situation, right, the electric environment in which we considered these effects, that environment was static. And so whatever environment was set up is maintained. So electrostatics. What we didn't really allow to happen is charge sort of en masse to move through a medium. We have been talking about charges at rest. Now we need to, if we're going to develop a model of electricity, we need to consider charges in motion. And here in this particular topic, that's where we start our consideration of charges in motion. I'm gonna resist referring to it as chapter 25 because not all of us might be using the Young and Friedman book. It's chapter 25 in the Young and Friedman book, but it's the next thing we're going to talk about: current, resistance, and this terrible name, electromotive force. Horrible name for a important thing, but terribly named. We are aiming to talk about these things in this particular lecture. I'm not going to read to you. Here they are. That's weird. Got rid of the mouse symbol. Current and circuits, right? Electric circuits are crucial. Our first module is about electricity, and it's circuits that are really the big news here. Electric fields, we saw this in the last unit about capacitance. An electric field stores energy because an electric field is set up by a charge distribution, and it takes some work to put that charge distribution together. That work is then stored in the electric field, the electric environment set up by that charge distribution. And if we allow that sort of that force to do work, we can move energy from one place to another. And we can do that without the mechanical motion of moving parts. We can take energy from here, where we're storing it, say, in a capacitor, and send it through media over here, where we have some, I don't know, device, like a flashlight, a light bulb. If we can get the energy from the battery to the light bulb in some kind of cyclical way, then we can continue to light the bulb for as long as we have energy available. Circuits are everywhere, and they are the thing. This is why we are interested. This is why we were interested from the very beginning in electric charge, although we didn't know it, you know, when we first observed electric charge, we didn't know that this is where we were headed. But it wasn't too long, but, you know, after realizing that if you, you know, braid a glass rod with silk, it has a particular behavior, that we started to say, well, hey, can I do something with this? What now that I have these charges stacked up on this glass rod, now what do I do? What is there something useful I can do with that? And that here's where we start that. Just like we did when we started with electric charge and field in the first place, we have some definitions to cover. That's basically what this particular lecture is about, is defining some things. Current is a motion of charge from one region to another. How much charge flows through a particular region divided by how much time it takes to do that. The rate at which charge flows, that's current by definition. Okay, so what is that in terms of actual charges moving through a medium? Now, the medium has some cross-sectional area A. And on average, altogether, let's say there's a total number n charge carriers, particles, charged particles that are moving. They occupy a volume. So what is their concentration? Lowercase n. How many charged particles per volume? Volumetric population density of charged particles. Okay. If we subject positively charged particles to an electric field E, they are pushed to the right. They are pushed to the right. Suppose that they do so at constant velocity for some reason, or maybe average velocity, that each one is maybe moving at a slightly different speed, but that if we average over the whole collection, on average, they're moving to the right with drift speed v sub d for drift. All right, so how many of them move through a region? The rate at which charge flows through an area. All right, so the region, if we know the volume concentration, we need to know the volume that we're talking about. Let's consider a volume A dx. It's the cross-sectional area times the thickness. That's a volume. How many charges are there per that much volume? Well, we multiply by the concentration. So how much charge is it? Well, each one of these charge carriers has, say, some charge Q. Charge per particle. And we take that and we divide by, because the definition of current says that we take the charge that moves and divide by time. So this is our d capital Q. We divide by dt. But dx by dt, that's v. So that's where this relation comes from. Charge carriers per unit volume moving with speed v sub d. Cool. We define the direction of current this way, according to the motion of positive charge carriers. Now, in metals, It's actually the electrons that are carrying the charge and moving in a current, and they would go opposite the direction of the electric field. Note, I was about to sneeze. Note that because this is a magnitudinal equation, it has no direction. Charge per time should be scalar. So this is the correct equation, whether we're talking about positive or negative charge carriers. We're taking the absolute value, the magnitude of the charge per particle. Sure, the electrons are moving the other way with some speed, but we define the current as in the direction of positive charge carriers. Current points in the direction that positive charges would flow. Sometimes we have both, right? In an aqueous solution, maybe we have positive and negative charge carriers that are free to move. And we would find the net current by talking about the current of the negative carriers and the positive carriers. It's a little bit weird to think about the current as the one way, regardless of what kind of charge it is. If we're going to tie the current direction as our conventional current, if we're going to tie that to the direction that positive charges would go, then we're tying it to the direction of the electric field. And it makes a certain amount of sense to try to define a directional current. And as long as we're just defining things, if we make this medium larger, if we increase the cross-sectional area A, we end up with more current without actually changing any of the reasons for there to be current. The electric field is the same. There is the same volume concentration of charge carriers. Like, there's no other effect on the current than just, well, we made the highway bigger. Now there are more lanes. So we might be interested in sort of controlling, defining away that particular effect. And we could talk about current per cross-sectional area. So like the cross-sectional current density. How much current per unit cross-sectional area. We keep using this, like how much of a thing per something else. We did that all 4 units. So we'll do that again here. I'd like to define current density. I'd like to define it as a vector so that it points in the same direction as the electric field. Okay. Now it looks like it has the same direction as the drift velocity, but it doesn't, because there are no absolute value bars on Q. Here, if the drift velocity is to the right, but the charge carriers are negative, you know what? Let me go back to the other slide. If the drift velocity, let's say, is to the left, but the charge carriers are negative, that means the field points in the other direction. And we define the current density so that it points in the same direction as the electric field that creates the current. The drift velocity is to the left, but the charges are negative, so we use the opposite direction, and we end up talking about a current density to the right, which is the same direction the field was pointing. vector current density. The magnitude of J, the magnitude of J is the current divided by the cross-sectional area. Because both of these things are scalar. And we define a vector current density according to the charge, the polarity of the charge and the direction we're going. Okay. What current density results from a particular electric field in a particular medium? So we set up a particular electric field from one side to the other of this, I don't know, this pipe, this conductor, and it's made of something, some substance, right? So it has some, and we can tell the difference, right? Materially between gold and steel and iron and copper, like they all look different. They all, think back to 231, they all have different thermal conductivities. So that I can't imagine that they would all behave the same way when subjected to the same electric field. And the thing that we use to keep track of that is resistivity or conductivity, depending. If we have an electric field magnitude E, I expect that to correspond to a proportional current density. What's the constant of proportionality? I'll use the symbol gamma for conductivity. How good is this particular material at conducting electric current? We set up an electric field and we get a proportional current density response according to how good this material is at conducting charge. Said another way, it requires so and so much electric field strength to get a unit of charge density according to the difficulty we have moving charge through this particular medium. How much field do we need per unit current density is a measure of how hard it is to push charge through this medium, and we'll call it resistivity. Conductivity, gamma, is the reciprocal of resistivity. Okay. So we need to set up an electric field so and so strong to get a current density J according to how much this material resists charge moving through it. Resistivity. What are some common resistivity values? I'm so glad you asked. Here are some. Resistivities are given in units of that. Ohm meters, OHM, ohm. Ohm meters. Now we can tie that to, we can tie that a little better to units we're more familiar with. Let me go back a slide. The dimensionality of rho. Now, electric field is volts per meter, or newtons per coulomb. And I'm thinking about newtons per coulomb because this has to do with, the J has to do with charge and current. Well, what the hell is the dimensionality of J? Hold on, I gotta go back a slide. J should have the units of current per square meter. So what are the units for current? Hold on, I gotta go back a slide. Charge per second, because dq per dt. Current has the units as dimensionality, charge per time, so it has the units of coulombs per second. We can define that as amperes, or just amps. 1 coulomb per second is 1 amp, 1 ampere of current. Okay, so I is coulombs per second. So J is coulombs per second per square meter. Coulomb per second meter squared. Okay, so coulombs per second meter squared. Okay, so the, oh dear. Newtons per coulomb, but then we divide by coulombs again. That's not gonna work. That's gonna give us coulomb squared in the denominator. Maybe volts per meter? That's possible. That's all right. Let's try volts per meter. I'm just trying to get some nice cancellations here. Volts per meter. So we got volts per meter divided by coulombs. So we switch it, meters squared seconds over coulombs. So we've got volts, meters, seconds per coulomb. Okay. Trying to figure out where we got ohms from. But this coulombs, this is seconds over coulombs, is the reciprocal of the units for current. So I'm saying I lost my unit tracking squiggles. Volts, meters per amp. If we compare this expression to the expression on the next slide, calling it ohm meters, it looks like an ohm, symbol omega, is a volt per amp. That the unit ohm is a volt per amp. Hopefully that connects to something that we see at some point here soon. That's, I mean, this is true according to our definitions so far. This appears to be made up. So hopefully we get to some point where we say that ohms is related to volts per amp. Hopefully. Volts, it's electric potential difference. It's related to energy. Energy per unit charge. In amps is charge moving through per time. So this is interesting. That's a cool interpretation. This is a slide about rho, and I'm just going to write over the text here because volts per amp. No, volts is energy per unit charge. And amps is charge per unit time. So this is potential energy time. That's kind of neat. Potential energy or work done. That's pretty cool. Question mark. Because of the really high difference between these resistivities to the -8 and to the +11, that permits the structure of circuit boards that we're familiar with. We can put these conductive traces so close together on the substrate, the insulating board, because the resistivity of the insulating board is so high compared to the conducting traces that no current is going to flow anywhere we don't want it. Like almost no current, and not enough to make a difference. That it's going to flow along the direction of the conductive trace and not anywhere else. So the fact that there's so big a range in the resistivity of different materials that permits circuit board construction that we're familiar with. Resistivity, the property of the, I don't know, freeness, the degree to which the material itself impedes the motion of charge. And we might expect that changes with temperature, because temperature is a measure of molecular kinetic energy. The greater the temperature, the more energy there is, the less able your average atom in the solid is able to hang on to its energetic electrons. The freer the electrons are, the more they can move through the metal. So we expect, I think, some temperature dependence. And yes, we can talk about the resistivity at temperature relative to some reference according to some temperature coefficient, the degree to which the resistivity changes with temperature. Is the relationship actually linear? No. But it's close. We could talk about a region in which it's close enough where we can linearize the relationship between temperature and resistivity, and we can tabulate those values. Someone has done that work for us. Of note here is this value, that it's negative. It's negative because graphite is a semiconductor, and that is the kind of explanation that I just gave about how resistivity changes with temperature. The more, like, the thermal excitation of the molecules in graphite makes it easier to move them around. In metals, other conductors, it appears to be worse as temperature goes up. Metallic bonding is fundamentally different. The metal in the crystal lattice for a metallic solid is they share electrons pretty freely anyway. The more energy there is, the more thermal energy there is, molecular kinetic energy, right? The more agitated the medium is, and the more likely these electrons that are in this sort of soup around the atoms, the more likely those electrons will collide, that the excited atoms will get in the way of the motion. So for metals, the cooler we are, the happier we are as far as electric current is concerned. Interesting. Superconductivity is another step above, another step beyond. If we can, some materials, and we are actively engaged in a search for more materials that evidence this phenomenon, we would like to push this temperature higher. Right now, it's we're talking about hundreds of Kelvin, which I suppose is workable, but it's still very, very cold for like normal everyday use. In order to get any kind of superconductivity, we're talking about like liquid nitrogen, liquid helium. Like, these are not everyday cold temperatures. A room temperature superconductor, that would be a huge breakthrough. Huge. At some temperature below this cutoff, the critical temperature, the resistivity drops to 0. Not close to 0, 0. And if we establish a current in a superconducting loop, it will persist forever. There's nothing to slow it down. There is no resistance, no resistivity. Which explains why we're after it. If we can get a current to run forever in a room temperature thing, then we can use that to do all sorts of things. It's just so far it requires colder temperatures than are, workable. Technically, our relationship that we defined before, that rho is E over J, technically, that presumes a linear relationship between, well, not technically, it does presume a linear relationship between electric field and current density. Not every material evidences that linearity. Sometimes the relationship is much more complicated. That the resistivity, maybe that this is a thing, but that the resistivity isn't constant. In other words, so that this is not a constant of proportionality, but there's a relationship between E and J that depends on a whole bunch of other factors. If, as is true for conductors generally, it is constant, that the resistivity is essentially constant for, a relatively small range of temperatures, then we can write this, and this is a constant. So what is this? Well, hold on. The electric field along a conductor is related to the line integral of the electric field. And if we go in the direction along the length, we just start talking about E and L. The current J is current over cross-sectional area. So put this together with this, and we end up with E is V over L, J is I over A, and we end up saying V A over I L, that V over I equals rho L over A. Wait a minute. V over I, that's volts over amps. We've seen that unit before. Yeah, volts over amps, that's electric potential divided by current. That's what I just wrote. This must be ohms. Which means this expression has something to do with the resistance of this material to electric current, because it's associated with the resistivity. Okay, cool. What do you want to call it? Let's call it resistance. The electric potential difference across a conductor that is carrying a current I is proportional to its resistance. This is true. Think of this like, call it Ohm's law, but think of it like the ideal gas law. It's true in abstract. It's true on paper that the relationship between potential difference and current is linear and proportional according to the resistance for a really well-behaved thing. Conductors, like monatomic gases, are pretty close to ideal. They behave pretty well. Hence our defining this in the first place as a linear relationship. If rho is constant, then we have this, and what we have essentially is a conductor. But, well, we have an ohmic device, some sort of electrical element that for which the potential difference across it is proportional to the current through it. In other words, it obeys Ohm's law. Actually, more than the ideal gas law, I think of this like a spring, because it looks a lot like Hooke's law. Not every spring obeys Hooke's law, always, at all stretches. Not every conductor obeys Ohm's law at all voltages or currents. But there's a regime in which a spring does obey Hooke's law, and there's a regime in which a conductor obeys Ohm's law. The more a conductor obeys Ohm's law, the more ohmic it is, and the more of like an ideal conductor it is. Resistors are essentially conductors, which doesn't feel like a fantastic name for them. They are conductive elements of specific resistance. Their job is to specifically, right, in an explicit and intentional amount, resist current. How much a resistor resists current is related to its resistivity and its size. Okay. In order for easy manufacturing, most resistors are pretty well standard manufacturing sizes. The wire within them is, different geometries exist inside this sort of like ceramic or plastic housing that we're doing. So it's hard to know at a glance, well, how strongly does this one resist current? And that's why they're manufactured and then painted with color coding so that we can tell at a glance, well, with a little bit of memorization, we can tell at a glance what the resistance is of this particular circuit element. 57 kilo ohms with a tolerance. Could be plus or minus 10%, which sounds like a lot. 5, 7, 10 to the 3. 5, 7, 10 to the 3, and a silver tolerance is 10%. How am I ever going to remember that? Well, we look it up in a table. So yeah, we've got our resistor with its color coding, and then we look at the table and we say, okay, red, brown, black, silver. And then we go and then we look at the table. Red, brown, black, silver. 10% tolerance. So this is a 21 ohm resistor, plus or minus 10%. I remember the order of these colors with this mnemonic device. I don't know. It's like Roy G. Biv, but longer. Bloom better roses on your rounds by very good watering. It's not very good grammar, but it'll do the job. But yeah, we can look this up in a table. No big deal. Whoops. What happened here? There we go. For an element that obeys, a circuit element that obeys Ohm's law, a graph of potential difference, voltage versus current, or current versus potential difference, whichever way you look at it, is a straight line. A element that does not obey Ohm's law is non-ohmic, and its graph is not a straight line. Also, its behavior may be different. It might not be a symmetric parabola or anything. It might be that there's some directionality. If we talk about a current one way or a current the other way, that we get a kind of a different behavior profile. Something like this we might call a diode. Okay. This electromotive force. Electromotive, I'll give you. Motive, motion, electro, okay, so it's the electric motion, right? We're talking about charges in motion. If we need charges to move, we need oomph. Oomph. Which is a, I don't know, so like a made up word, an onomatopoeia that has to do with effort or, you know, yeah. If I want to get these charges to move, I push them harder. If I want to get them to move more, I push them harder. I need more oomph, which is about as good a name as electromotive force, because it isn't force. It's about as precise as oomph. Electromotive force, which we abbreviate as EMF, which would be pronounced, it's conventionally produced EMF. But if you just read it as a word, it would look a lot like oomph, right? Oomph. That's the kind of the way I'd like us to think about it. It's not a force, it's oomph. Right? And even our slide is calling this out. This is not a good name for this. It is not a force. It does not have the dimensionality of force. It has the dimensionality of electric potential. And we call it electromotive force. The metric unit of oomph is the same as for potential. Yeah, it's the volt. A typical battery has an EMF of 1.5 volts, which means if we can keep track of the unit here, joules per coulomb, energy per charge, that a battery does 1.5 joules of work on every coulomb of charge that it moves through it. The symbol, this is not the symbol I want to use, a script capital E. On the next slide, we'll see another version of a symbol that I don't want to use. I'm going to write it like that. And this extra curl up here is important for me because I've started using this symbol for epsilon. Epsilon was that, but that started to look like an E, like a capital E. So then I started writing epsilon this way, and then they went ahead and gave me this slide and said that this is a script capital E, and I don't think that it is. But then they gave us the next one, and that looks a lot like my modified epsilon. So if I want this symbol, I'll make sure it has an extra curl at the top to set it apart from epsilon. A real battery has some measure of internal resistance, like an engine has a little bit of internal friction. The effective oomph we get out, the voltage, the potential difference between the two terminals, how big a electric potential environment can we set up? It's the terminal voltage. It's related to the oomph of the internal chemistry that's doing work on charges. If it's some kind of redox reaction, then okay, there's a certain energy of reaction associated with that particular chemical reaction. There is a fixed amount of electromotive force. It is reduced on its way out by the internal resistance according to the current that we are pushing through. So the actual like effective current causing stuff is VAB. It's reduced from the EMF of the internal chemistry by the internal resistance. Since we're considering electric circuits, we are going to need a way to represent sort of in quick diagrams, kind of like a free body diagram, but for circuits, a shorthand for how to draw a circuit, because we don't actually want to have to go get a picture of the actual electric circuit every time. A battery, or better yet, an EMF source, just the symbol script E. If we want a battery, like a real one, we'll often draw it as an EMF source with sort of packaged with its own internal resistance. And we can put the resistance on either side, it doesn't matter. A resistor, which is, again, a conductive element of a particular resistance. That's all it is. We'll draw with this jagged kind of thing. And for now, that's enough. We have devices that measure potential difference and current, and we'll use a circle with a V and a circle with an A for potential difference and current. Note that we don't use an I. It isn't measuring anything with the unit symbol I, it's measuring amperes. It's measuring current. Okay. Electric potential is in order for this to be a circuit and like a loop that we could go over again and again and again according to how the battery is pushing things. We are pushed uphill, up an electric potential hill by the battery, and then we travel along the wire, which is assumed to have zero resistance. It's a perfect conductor. Again, an idealization, but compared to the resistor, it's not a terrible one. Compared to 2 ohms, 4 ohms, the resistance of this little bit of wire is in fact negligible. So we don't really lose any energy per unit charge, which means we don't lose any potential going through the wire. On our way through the resistor, we do have to lose some energy because we have to push through. We have to do work against that resistance. It's like friction. It's like electric friction. Another section of wire, another resistor. And then if there's nothing else, we need to be back where we started so that we're ready to be lifted up by the battery again and that it's actually a circuit. Let's define power as potential difference times current, the rate of energy transfer, work done per time. Work is charge times voltage, and charge per time is current. So that's where that relationship comes from. The power delivered to, supplied to, or dissipated by, extracted from a particular circuit element is, there it is right there. The potential of the battery is the EMF of the battery minus I times the internal resistance. And we're going to multiply by I, so we end up with that. Converts chemical, say, energy to electrical at a particular rate, particular power, but some energy is dissipated in that internal resistance according to that rate. So the difference is the supplied power, the power supplied by this battery. Check out this video tutor solution. This is a sort of a conceptual model for why it's only a drift velocity we're talking about when we talk about current, and why it's not the case that the electric field accelerates the charges, which is what usually happens. The reason is that we keep making collisions, as we've already talked about a little bit, collisions with the atoms in the crystal structure of the metal. Those collisions interrupt the acceleration that might be caused by a standing electric field. On average, because we are being, if the field is to the left, the electrons are being pulled to the right. On average, after a bunch of collisions, the electron will end up further to the right than it would have otherwise if things were just allowed to be random. This is a model for the reason that we only talk about a drift. We're not actually talking about the actual speed of the electron. We're talking about the overall motion opposite the electric field as a sort of a net result of many collisions with atoms in the crystal. Check out this video tutor solution. Click that link in the slides. That will be live. And believe it or not, that's all I've got. Thanks, everybody. See you next time.